Sıradaki konuşmacımız PANDUIT'ten Zacharias Baveas. Kendisini alkışlarınızla sahneye davet ediyorum.
Good morning, ladies and gentlemen. Thank you very much for being here. My name is Zacharias Baveas, and I'm working for PANDUIT, a US company. And I'm glad to see, with reference to the previous presentation, that all the well-known and experienced cable manufacturers have more or less common approach on AI era. So today we're going to talk how AI, which is the big topic these days, is impacting the physical infrastructure within the data centers, and what are the main concerns we need to consider designing and deploying AI data centers. So it's in fact, everybody is talking about AI, it's a big trend, and as you listened before, is the main driver in terms of power and computing and data center investment. You see where we are today, 2025, going to 2030, in only 5 years from now, the capacity is going to be 3.5 times more. This means power, cooling, computing, networking, everything. And the main driver of this investment is the company that is producing GPUs, NVIDIA. And the benefit of a GPU or AI is the computational capability. So moving from CPU to GPU, what we're achieving to exponentially increase the computational capacity per system, but also be able to run parallel processes. This is the biggest advantage. And you can see the comparison from the first generation GPU launched a few years ago to what is available, what was made available in 2025. We have a computational capacity exponential almost from 5 to 20 to 72. This is a very big number. And the roadmap from NVIDIA continues to grow exponentially up to the 2030, which will be 100 times faster. So to support this great computational capacity, we need to provision the respective network infrastructure to support this high-speed performance and processing. So to do this, we see a big shift from what we used to have on a traditional data centers, 10 gigabit, 25 gigabit, 25 gigabit, 50 gigabit, all the way up to 800, 1.6 tera. And you see, this is where we are today, where for all AI deployments, the 800 gigabit is dominating. This is the reference designs launched and supported by NVIDIA and all the network vendors. And as was said before, we start seeing from next year 1.6, and already the international standard committees have on works the 3.2. So today, as we speak, all AI architectures and deployed are based on 800 gigabps data transmission, point to point, and this is deployed with the parallel optics. For every single connection, we require an MPO trunk, as was mentioned before, also APC angle to support these high data rates. So what is the impact of this? And what is the architecture of AI system? To achieve this LAN rate and high computing performance, we need to connect all GPU systems one-to-one. We need to eliminate what we call the latency, and we need to eliminate also the layers of networking to avoid having multiple hops that introduce latency. So an AI system today consists of 4 networks. And an AI system also, as it is designed today with available architecture, and also it will be the same for NVL72 systems, it's a pod or a cluster that consists of 32 nodes. The NVL144, it will be double of that, but today we speak about building blocks of this number of GPU processing units. So if we have a gigafactory, we multiply these pods and we have after 4 ports, to introduce another networking layer to interconnect. So we do have our backend system, which is all GPUs to GPUs communication. There is also the backplane communication within each server that GPU to GPU is communicating, but we need also the communication from physical host that has this 8 GPUs to other GPU physical host. We do have the front end, so GPU or an AI system cannot exist as a standalone. It has to communicate to pull data, push data from our corporate network. We call this the front end. We need to have a storage where we store the generating and processing information. And this very high-dense environment, we need to have to control it and do operational actions, the out-of-band management system. So to put this on a perspective, we would like to show you, this is based on existing GPU physical chassis, GP2 B200 on H200. This is the backplane of a GPU server. We see we have, excuse me, the GPU to GPU interfaces, which is a transceiver that supports 800 gigabps, and currently the most common and less efficient in terms of power and cooling and cost of electronics. It is deployed with 2 times 400 gig interfaces. Then we have the red highlighted is the front end, how we communicate with our existing networks, and the other 2 interfaces with our storage network. And then still, although AI is dominated by fiber, we have the management interface, the green one, which is a gigabit communication over copper. The new systems coming out in the near future, 2026, 2027, will most likely have 2 management interfaces for redundancy. So to put this to a perspective, a pod or a cluster of a GPU consisting of 32 physical hosts or GPUs, think about it, it's a cabinet row, and in a data center you will have, especially in gigafactories, multiple of these pods. It requires this fiber connectivity for GPU to GPU communication. So every single line you see here represents an MPO to MPO communication that allows every GPU to communicate with any GPU in 1-to-1 ratio. So you see that we have our processing units, GPUs, we have our leaves, and then we mirror the ports to the spines to achieve this high performance network. This is what we call the back-end network, which is GPU to GPU. Then on top of it, we add what we call the front end, how these systems communicate with our corporate network, with the existing infrastructure we have. And then on top of it, we have to add our storage network. Today, the storage network may be in the range of, depending on the topology, the technology the customer has deployed, starting from 64, going all the way up to 200 gigabit. And at the end, on a copper connectivity is how we connect all our systems for the out-of-band management. It's very unlikely these days to see technicians sitting at the back of a GPU cabinet issuing command lines. Everything is done remotely from a network operations center. So you see this challenging diagram, and if you try to put it in a perspective, this is just across a cabinet row that you have 8 cabinets and maybe another 2 cabinets for networking. So the amount of connectivity, fiber connectivity that goes there, and the criticality of every single connection once you have this system up and running, it's very, very crucial, very important. As was said before, and we are aligned with this, very, very high computing and demanding system, very expensive. So you don't want your customers or your organization to make this investment and have these systems sitting in a data center and underperforming due to the poor physical infrastructure. Everybody is talking about the challenges on power and cooling, which indeed are big, because we are talking about 20, 30 times higher plus power and cooling capacity. But as you can see, the connectivity, the physical infrastructure is equally important. So AI, everybody's talking about AI, but everybody's puzzled and worried how to deploy AI. So it looks, I could say it's a cloud, okay, but it looks quite scary, and we need to think what are the main challenges. So we talk about exponential increase on power and cooling and connectivity. So cabinet, where we host our AI systems, it plays a very crucial role. The existing systems, we do have the opportunity to do what we call the rack and stacking on site, but the new systems coming out that have 3-4 times higher power consumption, different cooling requirements, direct-to-chip cooling, and connectivity will be like a pre-configured cabinet. And this puts a challenge also on the weight. We start see deployments that you cannot anymore tolerate having raised floor. We're talking about cabinets that may go up to 2 tons. So static becomes very crucial, and we see all these new data centers, gigafactory data centers going on a slab without raised floor. Then power consumption and cooling. When we have cabinets based on the roadmap announcement of NVIDIA that go beyond 120, 150 kilowatts per cabinet, you cannot anymore support this with the traditional AC PDUs power distribution. We have to deploy and adapt completely different concept of DC power cells. So different skill sets, different way of distributing the power. We're going to have DC power distribution at the back plane where you snap in the service. So different concept designing the power distribution. According the same way is a cooling. Today the GP200 and 800 systems can still be air-cooled when we have a distributed architecture we see later. But all the new systems, NVL72, NVL144, are only liquid-cooled technology. We cannot support them on a traditional air-cooled, which means the data center needs to be designed and built in purpose to support these loads. Cooling, will it be rear door heat exchangers up to 60, 70 kilowatts? Then going beyond this, we require the manifolds and liquid cooling direct to chip. But although everybody is talking about direct to chip cooling, DLC's technology, this is applicable for GPUs and servers because they have the cold plates. All the networking coming to support this communication does not support DLC. So we will still need a traditional air-cooled system. So it's going to have a hybrid environment. And at the end, we have the connectivity that we mentioned, which is an equally very, very important factor and crucial. And as we show the amount of fiber connectivity going in such a small footprint, it requires the correct provision of pathways. We're going to see in the data centers multiple layers of pathways to support this increased density and much wider. And as we talk about fiber connectivity and high data rates, the way we install the fibers, the way we bundle the cables, the bend radius of all these bundles of trunk cables, it's very important to maintain and provision the right performance of the fiber. So as a company, PANDUIT, we have deployed a blueprint. We have designed a blueprint that's been approved by NVIDIA. You can either do it in a very quick, okay, and cheap way. Actually, initially, NVIDIA on the first reference designs was encouraging InfiniBand and direct connection point-to-point. After the first deployments, they realized that direct connections point-to-point is not so scalable and easy manageable. And as was said from Comscope before, more and more the market and NVIDIA themselves, they start pushing from Ethernet. Why? It's easier to deploy, cheaper, and more scalable. And because of the technology evolution, we start seeing gradually, and very fast, Ethernet catching up InfiniBand in terms of performance. So this is a real picture from a real environment where unfortunately the customer had to rush, and although it spent millions of dollars to deploy GPUs, you don't have to be a physical infrastructure expert to see the challenges that you have with this, let's say, not very professional approach to deploy the physical infrastructure. Or you can do it in a more structured and proper way where it will help you to have a better management in case you need to troubleshoot, easy to troubleshoot. And don't forget, we used to say in the past that the life cycle of an IT infrastructure in a traditional data center was between 3 to 4 years. AI, I would say it's a race. Who will have the most optimum system, the most well-performed system to be competitive, the customer to be competitive and be able to be differentiated from the competition. So we're going to see that although it costs a lot of money, we're going to see the life cycle be slightly shorter. So if you put the infrastructure, you need to make sure that it's ready to support what comes next in the future. So as a company, we have an application guide, which is also listed on nvidia.com, approved reference design, how to quickly and fast deploy the physical infrastructure depending the architecture and the layout. You saw this schematic also before. This is how we spread the load with the existing NVIDIA GPUs models, the H200 or B200, why you see these cabinets being underutilized is in order to control the power consumption per cabinet and be able to cool it with a traditional air-cooled solution. We could add additional hardware in its cabinet, but this would drive the power consumption per cabinet higher, and the air-cooled system wouldn't be sufficient. So this is how we mirror all the connectivity from each host to the top of the cabinet, can be either inside the cabinet or outside, and how we mirror this on the aggregation cabinets where we have our spines and leaves. And remember, we have 4 networks. This is the GPU to GPU communication, the back end, our front end with our corporate network, fiber, our storage, again fiber, and then the out-of-band management system. So we have developed some blueprints to facilitate our partners and customers how to well select the products, how to organize, what are the correct components, how to mirror within the compute cabinets, how to mirror the compute cabinets to the network aggregation cabinet where you have your spines and leaves, and how you can go from the network to the front-end infrastructure where you have your storage and your corporate network. This is how it would look like in an liquid-cooled topology. So the same amount of connections in a smaller form factor servers with less GPUs, with double the power capacity, but still connectivity, as was mentioned before, represent the same. And this is the NVL72, where you have 2 clusters, 4 plus 4, where the form factor of the host, the physical host, is reduced to 1 or 2 systems, 4 GPUs. In between, you have also the NVL chassis that it support, because this host, physical host, doesn't have enough space at the back plane to do this GPU to GPU communication bus. It's support here, but still you need a traditional point-to-point fiber trunks for physical SASE to physical SASE to deploy. These systems here are not going to be rack and stack on site. It will be regardless who will be the vendor. It will be pre-configured cabinets, liquid cool with direct-to-chip cooling solution with manifolds, DC power distribution, power cells. We're moving away, but still the communication layer, the physical layer is there. And as was mentioned, the quantity of fiber links is exponential. To put it in a perspective, and if you could visualize, this represents us a small row where you have 64 GPUs. Think about the gigafactories everybody's talking about. It doesn't have to be 100,000 GPUs, but any data center built on purpose to support AI processing is going to be multiple pods, clusters of these. The NVL 144, it will be double of this, but still will require the same amount of fiber connectivity. And as we start building more and more such pods, we start introducing the additional networking layer and how, in order to support this intercommunication in LAN rate between the different pods. So we have a complete set of products where you can very quickly mirror the links from server cabinets hosting GPUs to network cabinets. Talking about high density environment, in theory, everything looks nice, but when it comes to the deployment and operation, there are quite a lot of challenges. So all our products on MPOs have integrated what we call this push-pull feature, where you can very easily connect and disconnect on the field. So with this, I would like to thank you very much. We have a booth outside in the exhibition area. We'll be more than happy to come and meet us and have a dialogue and discuss in more details if you have any questions. Thank you very much.